Last month, scientists announced that they had detected something never seen before. Two massive neutron stars colliding with each other, triggering a colossal explosion. It marks the most dramatic example so far of a new type of astronomy that focuses on brief transitory events that happen so fast they're almost impossible to detect. Welcome to the spectacular world of astronomy that happens in the blink of an eye. We're used to thinking that the universe operates on timescales of millions or even billions of years. Most change happens with imperceptible slowness. We have now discovered a whole catalogue of events, like the neutron star collision, that happen on much shorter timescales, seconds or even milliseconds. Tonight, we explore this world of transitory events. I'm here at Jodrell Bank to find out the latest theories about the most mysterious of all transitory events, fast radio bursts. We'll hear more about the recently detected neutron star collision and gravitational wave. Chris joins astronomers attempting to detect gamma ray bursts, the most powerful short-term event that we know of, to see just how different this kind of astronomy is.
We could say possible burst if you want.
I don't know what I want. I don't know.
And here it is.
And Lucy Green reveals that some dramatic, rapid phenomena can occur much closer to home. But we start with Chris, who spent a couple of days with scientists attempting to detect an elusive gamma ray burst.
Astronomy used to be about staring up at the unchanging heavens. So this search for transients, things that go bang in the night, is truly revolutionary. But it all depends on astronomers' ability to monitor the whole sky. So I've come to the University of Leicester to see how this is done. This is the UK base of SWIFT, a space-based telescope designed to search for GRBs, gamma-ray bursts. Brilliant flashes of light that last just for a few seconds. It's thought that some of them are caused by neutron stars collapsing into black holes. The problem is that they're rare, and so SWIFT has to do two things. First, it has to scan the whole sky to spot when a GRB occurs. And then second, it has to swerve to get the data before it disappears.
So we're here because you're controlling the spacecraft. This is not what I thought mission control would look like. So what's your role?
I am one of a team of observatory duty scientists, ODS for short. Everything is so well designed now, because as long as you have access to a computer and you can log into the relevant computers, we can do everything.
So how quickly can SWIFT respond once it's detected something?
Quickly. So the maximum speed we can slew at is about 1 degree a second. This typically means that for most gamma ray bursts that we detect, we'll be on target between 1 to 2 minutes.
And that's important for the science.
It is, yes. Gamma ray bursts may be the brightest explosions in the universe since the Big Bang, but they fade really quickly, so you have to get on there as fast as you can.
If you're not swift, you miss it.
Exactly.
At 8:33 a.m, there's an alarm. SWIFT has spotted something. Phil Evans, the BA, or burst advocate, immediately starts to analyse the new data. and Kim gets on the line to her counterpart at the Goddard Space Flight Center in Maryland to see if they've noticed the same event.
Hi Amy, it's Kim and the Leicester crowd. Yes, it's NGC 224 that is the nearby source.
No, it looked like it could be something in there though.
You mean that the one big spike before the
Yeah.
Yeah.
Could it be an SGR in M31?
I mean it's less than 6 sigma though.
Yeah, and I guess XRT didn't see anything.
Okay, we've now got a spur
Yeah,
NAC.
it's
so-
got lots of stuff in it, but no point source.
This feels almost like something from science fiction. Within seconds, Phil has more information about the location of the source. Did I hear it's M31, the Andromeda Galaxy?
Yeah, so the thing is M31's full of sources. So we found an
enormous on the sky as well.
It is as well, which doesn't help. So we found an object which is a known object, which is that one there in this image. So there's the core M31's off here.
Right.
The issue is this just because that object is there, or is it suddenly got brighter? And for some reason, I'm not getting a brightness of this new source.
The problem is, the signal is very faint. And what's more, it's buried in a galaxy chock full of other sources of radiation.
A sort of vague source. The automatic system didn't detect anything, but by eye it looks like there might be. So they were trying to see if they could figure out what was going on. I'm assuming the answer was no to that.
I haven't yet managed to get a light curve. I know why. It's because it's
Okay, no,
films
that's
of
not what
flash.
I was asking. Well, I mean, we could say possible burst if you want.
I don't know what I want. I don't know.
You're the BA. I'm going to leave this in your hands.
No, give us a second. Let me just think.
After more discussion, Phil and Kim decide the trigger probably wasn't a GRB, but instead came from some other source within the Andromeda Galaxy. So, Kim, what just happened?
So, Swift triggered on something. We slewed round rapidly. We were on target in 74 seconds, so just over a minute.
It's impressive.
It then went on and showed us that not only had we detected one known source, we'd detected 5 known sources. So it took us about 45 minutes on that telecon. If it had been a real GRB, probably more like 15, 20 minutes.
So the satellite's back to its normal job and we're back to waiting for a burst.
Exactly.
A few hours later, the story changes again when Phil and Kim call the American team with their report.
Yeah, Jamie, this is Phil. Can I just mention this morning's event, because there's a couple of queries about it.
They've noticed that the same telltale signal was also seen by a second telescope called Fermi. More pressure now on Kim and Phil to come up with an explanation.
I realise that. But there's a possibility of something interesting here, so we shouldn't throw it out. My suggestion, if you could identify what that source is, then we could rule it out as interesting. That doesn't confirm that it's real, but it makes it a little bit more plausible. Agreed. Plausible. Yeah.
Well, that was exciting. It turns out while the team here were running about this morning, the Fermi Gamma Ray Burst hunting satellite also saw something. And so the fact that there was something seen by Swift and Fermi means it's worth going back for another look. So that's what the spacecraft's doing right now. For the next few hours, Kim and Phil are back observing M31 and reconsidering their data.
Continue monitoring this variable AGN to get a good optical to X-ray SED.
And later, they have a new theory. After running the numbers, they still believe that what they saw isn't a gamma ray burst. They think it's an unusual object bright in X-rays that's actually been seen before.
The object is called Swift J0243.6 plus 6124. Really sticks in the mind. It's named after the position in the sky. So this was first detected by Swift on the 3rd of October. We had a trigger and we didn't know if it was a new gamma ray burst or a galactic transient. So we kept collecting data and the X-rays stayed bright. Now for a GRB, the X-rays, the afterglow in the X-rays will fade fairly quickly over time. The fact that they stayed bright told us it wasn't a GRB and it was some kind of transient. So it's still getting brighter at the moment, so we may trigger again. We'll just have to wait and see.
Kim's day is over by 7 p.m. Any new activity now will come direct to her phone, and she'll have to deal with it at home. Which is, of course, exactly what happened next. A genuine gamma-ray burst was detected at 12:07 a.m.
So, just after midnight on the early hours of Saturday, Swift triggered on a GRB.
So what do we know about this burst?
It's a long gamma-ray burst, so this means it was a very massive star originally, more than 40 times the mass of our Sun, and it just got to the end of its life. So at that point, it all collapses in on itself, and as it does this, stars rotate generally, so everything's spiralling around in, and you get jets of material shot out. And if those jets are pointing towards us, Swift can detect it, and that's what we see as a GRB.
I can see now just how pressurized observing transient events is. And it makes sense, because with something that's over so quickly, decisions have to be made fast and often on the basis of incomplete data.
Gamma-ray bursts are not the only transitory event in space, though. Recently, astronomers have observed a new type of phenomena, shorter, more powerful, and incredibly elusive. Fast radio bursts. Unlike anything else known, these strange chirps of radio waves are only milliseconds long and have a unique characteristic sound, sweeping from high to low frequency. And their wavelength is at least 1 billion times longer than gamma-ray bursts, suggesting that they may arise from a different cosmic process. But what? I spoke to Ben Stappers at Jodrell Bank, one of the UK's key research centres for fast radio bursts, to find out more about this incredibly strange phenomenon. So, Ben, what are these FRBs, these fast radio bursts?
Well, fast radio bursts are these very short duration, just a few milliseconds of radio emission that are detected from far away by radio telescopes.
So how many others have been detected?
I think around about 30 so far, but we're discovering a few every month now.
So are there any other variations between them?
Yeah, so we think that the vast majority of them so far have never been seen to repeat, even with observations of many hundreds of hours, in fact.
But then, in 2012, the Arecibo telescope in Puerto Rico observed a fast radio burst that did something totally unexpected. There was a second FRB from the same source, and then more. Suddenly, this meant we had a chance to see an FRB happening in real time.
And one of the advantages of something that repeats is that we can actually go back and do more observing, and it's been possible for people to localize this burst. And what I mean by that is you can see exactly where it is in the sky and associate it with a host galaxy.
So it brings us to the million-dollar question. What actually are they?
A lot of people have been having a lot of fun coming up with theories of what these things are, and presently there's more theories than there are bursts. If we think that there are now two classes of these objects, where the repeater maybe is one type and those bursts we've only detected once are another type. The single ones might be associated with something cataclysmic, where the object itself is destroyed or the event is a one-off. So it could be something like merging neutron stars that are occurring, and there's also an idea that you have this thing called a blitzar, which is actually a very rapidly rotating neutron star. It's very massive, more massive than neutron stars should be, and eventually, as it slows down, it collapses into a black hole. And when that happens, it actually ejects its magnetic field. And these sound very exotic.
It does, yes.
But in the case of the repeater, maybe it's a newly born object called a magnetar. Now, a magnetar is also a neutron star, something that's spinning, that has a very large magnetic field, very, very strong magnetic field. And so the idea is that maybe in the birth event of these things, something happens that generates these fast radio bursts.
Well, it's fantastic to hear about a genuine astronomical mystery, and I'd love to come back as you get more information and really find out what they are. Yes,
I hope we can invite you back and be able to tell you exactly what they are.
That's been fascinating. Thank you so much.
Thank you.
What's particularly exciting about this new fast response astronomy is that these powerful transitory events don't just occur in deep space. They happen in our solar system too. Just think about our sun. The sun feels as though it hardly changes at all. But actually, if we look close enough, we see a very different story. Lucy Green explains how the sun is actually a treasure trove of spectacular transient events.
We all feel familiar with our local star. At 93 million miles away, the sun is still able to give us all the heat and the light that we need to survive. And today it looks absolutely glorious in this beautiful sunny sky. But to really see the sun, we actually have to go inside.
Because the best way to see what's happening on the sun is to look at it from space.
And here it is, the sun as seen by NASA's Solar Dynamics Observatory. It's a telescope in orbit around the Earth. These images are just a few minutes old, and they show not only an enormous range of structure, but also just how dynamic the sun is. And for example, over here, we see these beautiful, evolving, glowing arches of gas in the sun's atmosphere. And it turns out that these structures are actually key to understanding the entire sun.
Because they are shaped, like everything else in the atmosphere of the sun, by magnetism.
The inside of the sun is a swirling mass of electrically charged gas, and wherever you have moving charged particles, you have magnetic field. And the thing that I really love about magnetic fields is that they have an influence on the material or the stuff that's around them. To show that, I have some iron filings suspended in a fluid and a bar magnet. And if I put the magnet on the iron filings, they immediately respond and they take on these beautiful arch-like shapes as they follow the lines of force of the magnetic field running from the North Pole to the South Pole. And in the same way that the iron filings responded to my magnet, the gases in the sun's atmosphere respond to the sun's magnetic field. So here you can see these giant arches of gas in the atmosphere of the sun. Oh, look at that. There was a plasma flow shooting along these magnetic field structures. Now, underneath this arch-like structure is something that we call a prominence or a filament. They are exactly the same thing. This is relatively cool plasma lofted into the atmosphere of the sun by its magnetic field. But just look how it's moving. It's sort of shimmering and oscillating. Now, studying these plasma clouds isn't just an academic activity. They actually mean something for us here on the Earth as well, because occasionally they will erupt into the solar system. This is an eruption that happened just a few days ago. There is a filament structure here and it erupts out into the solar system. Now, to give you here it goes. So there goes the eruption. And it is an enormous structure. To give you a sense of scale, the Earth is about as big as this bright patch in the atmosphere of the sun here. So this eruption starts off already many times the size of the Earth and then expands to become many, many times bigger actually than the sun itself. And now you can see that enormous structure heading out into the solar system. And if these eruptions are Earth-directed, they slam into the Earth's magnetic field, shaking it up and triggering what we call stormy space weather, affecting our electricity networks, our high-frequency radio communications, all kinds of ways our modern technology is ultimately affected by these eruptions from the sun. The last transient phenomenon that I want to show you is something called spicules, and here we are. All along the edge of the sun are spicules. You can see these dark, sort of like grass-like features, or like the spines on a hedgehog, but waving in the wind, and they are the spicules. They are as tall as the Earth is wide, and they really are transient features because they only last on the sun for around 10 to 15 minutes. Today, they're viewed as being important in heating the corona of the sun. They transport gas from the lower layers to the upper atmosphere, the corona, which has a temperature of millions of degrees Kelvin, or millions of degrees Celsius.
Ironically, this part of the sun is an area astronomers consider relatively tranquil, and they call it the quiet sun.
But images like this from the Solar Dynamics Observatory has shown us that this isn't really the quiet sun at all. The quiet sun, in a sense, is dominated by all this activity.
Observing this transient solar behaviour is not just for professionals. Amateurs can relatively easily spot many of the phenomena that Lucy saw. Pete Lawrence explains.
The sun is one of the most rewarding objects in the whole sky.
But first, a word of caution, because looking at the sun under any circumstances can be extremely dangerous. It's very bright and it can permanently damage your eyes or equipment. So if you intend to use a telescope, you need to use a certified solar filter, because that will reduce the incoming light to a safe level. And remember to remove or cap your telescope's finder. Apart from the fact that it too could be damaged, the temptation to look through it could end with disastrous consequences.
Line the telescope up with the sun whilst looking at the telescope's shadow. That way, you won't look into the sun's glare.
So once you're lined up, you can start viewing. And the most obvious transient solar phenomenon is sunspots.
These are caused by intense magnetic fields, creating localized cooling. The result is a region that looks darker than its hot surroundings.
Now, through my white light filter, I can see there's just one tiny sunspot on view, but other days you can get more sunspots visible. But to see the really fast-moving action, I need to switch to a different type of filter, a hydrogen alpha filter. An H-alpha filter rejects all the wavelengths of visible light except those given off by excited hydrogen atoms. Now I've got the hydrogen alpha filter fitted, I've got some incredible detail on the sun's disk. I can see some dark filaments, that's cooler clouds of hydrogen in the sun's atmosphere. But the really impressive stuff is down at the bottom of the disk I've got here, because if I go down there and then boost the exposure, I can see some incredible prominences on the edge of the sun.
So remember, astronomy can be just as rewarding in the daytime as at night. But if you're going to get to know the sun, do make sure you observe it safely.
Observing brief cosmic events isn't only redefining how we do astronomy, it's also giving us new information about the universe. Which brings us back to that neutron star collision that made the headlines last month. Just as we were preparing to make this programme, news broke of an exciting new transient of a type that we simply haven't seen before.
Tonight at 10, an international team of scientists has discovered the effects of a collision between two dead stars, called neutron stars, which happened 130 million years ago.
The first sign was a gravitational wave picked up by the huge detectors at LIGO in America and Virgo in Italy. At almost exactly the same time, the Fermi satellite detected a gamma-ray burst coming from the same location. It's the first time that those two things, gravitational waves and a burst of light, have been seen coming from the same place. This detection triggered a secondary flurry of activity of other telescopes right around the world, including Swift, all scouring the sky for more information. All the evidence suggested that what had been seen was the collision of two neutron stars, the compressed cores of now dead massive stars, now ripped apart in an event of unimaginable violence. This turned out to be a kilonova, one of the biggest and most powerful explosions known. As well as being burst advocate on Swift, Phil Evans headed up Swift's observations of the kilonova. I persuaded him to leave his desk for a moment to explain what really happened, and how this event helps us understand how heavy elements are actually created. So this is a very exciting event.
Yes.
So what did you see?
Well, we didn't see X-rays, which was a surprise because
if you have a gamma ray burst, you normally, not always, but normally get X-rays. And with this thing being so close, it should have been about 12,000 times brighter than a typical gamma ray burst, so we were expecting something. We did see very bright ultraviolet emission, and that was a real surprise because if there's no X-rays, then where did the ultraviolet emission come from? There's no afterglow. And this is what led us to the belief that maybe what we'd found was not a typical gamma ray burst afterglow, but something new.
So so people assume that this thing is what's called a kilonova.
That's right.
These two neutron stars merging, and they have this unusual signature. Why does two neutron stars colliding produce light anyway? Why do we see it as a gamma ray burst? And then where does the ultraviolet come from?
When you get two neutron stars, now remember, these have got very, very strong gravity. You've got the mass of the sun, and gravity is proportional to mass, but crammed down into an area maybe 10 kilometres across, so the size of the city we're standing in right now, for example. So when you make the radius really small, gravity shoots up. So you get two neutron stars really close together, and they start off looking sort of round, and then they start to distort, almost becoming teardrop shaped, because each one is pulling really hard on the nearby side of the other one and less hard on the other side, and that change in gravity across the neutron star is enough to start to distort it and then eventually to rip it apart. So as it falls on, it gives off radiation, and we think that in a lot of events where you get stuff falling in, it's spiralling around in the disk, and as it falls in, you launch jets, so you get material that's blasted out the sort of the poles of the event, very close to the speed of light. But in a kilonova, you're seeing something very special, because as well as this material that's falling in and coming out in jets, you've got loads of material swirling around, very, very dense material, close together, full of neutrons.
So this is neutron star rubble?
Neutron star rubble, right, and it's neutron rich. And this makes it a prime site for something that we call the rapid neutron capture process. And this is basically one of the ways the universe can create elements heavier than iron. But when you do that, right, you make unstable elements and they decay, because radio, just like your uranium in your nuclear power station does,
yep.
It decays and that glows. And so that gives us what we call the kilonova, and it's the signature of the formation of heavy elements in the universe. So
your bright ultraviolet light that Swift was seeing from this event might come from the decay of new elements that have been created.
That's right.
And now we know where it comes from.
And now we know, at least, where some of it comes from. And we only know that because we saw this ultraviolet flash of light.
What all this shows is something very exciting. We can now actually watch the universe change in front of our eyes. And these events that happen in just seconds can have profound consequences.
That's it for this programme, from here at Jodrell Bank and also from Swift. But do join us again next month when we'll be presenting our Christmas special, getting back to basics to show everybody how to enjoy the night sky, including how to get started in astronomy, the best equipment to buy, and also how to enjoy the night sky with no tech at all. Do go to our website in the meantime and check out Pete's Star Guide and also great stuff we couldn't fit into this programme. In the meantime, of course, get outside and get looking up. Good night.
Stay with us here on BBC4 for Strange Signals from Outer Space with Horizon next.